So what are you said on the way out before he left that some people might have a test today or no? What topic are you on? And whose class are you in? Guys, okay. So you didn't have a test today, baby? No, okay. Oh, okay. Because I thought maybe we'd be starting the next chapter, but I don't know for sure. Hi. You're gonna have to be patient while I figure some of this out. I might need your help too. Let's see, we should probably have that on. Okay, okay, that sounds like what. I'll put this down. Okay, that's what he thought he might be on, so, okay. What's the visual? Oh, thank you, yeah. I need the visualizer. There it is. Oh, I forgot how to do this. I'm in the meeting, so I don't need that anymore. How do I switch this over? Let me go up there. Oh. Hello, thank you. How do I get this? Got that there. But I want this to be showing.
It's the code line.
It is, yeah, I'm filling in for James. Is this for 17A?
Yes.
Yeah, sorry. Yeah, you probably saw me sitting here the other day, and I wish I would have paid more attention how to get this thing going. Drag this back. It's 210. Okay. Automatically. Can you hear me if you're tuning in remotely? Hi, yes. Give me a second, everyone. I'm trying to figure out, does anybody know how this works? Before I go run and ask for help? No, okay. Because I got to figure out how to get this screen on there. Got it on me, but I don't want that. I want the screen. Oh, wait. Okay, so now I have that. Oh, hi, thank you. It's recognizing this. Oh, okay, you can't hear me. Okay. Yeah, sorry, I'm trying, if you're waiting, I'm trying to get the video to work. I'm Grant, I'm filling in for James. And I'm just missing one step here. Hi, thank you. How do I get that over? Wait, maybe I'm showing share screen. Now if I okay. All right. Give me 1 minute. I'm going to see if someone down there knows. This is my, I haven't been teaching in this classroom, so I don't know how this works yet, but I'll be right back. Luck with having it, there's nobody around. Isn't it always like that? What am I gonna do here? Okay, somebody can hear, but that can't see. What happens if I start my video? So I want to pin this. I'll make it big. Just quit out of this. Right, and set to mirror. That's too small. I want that. Oh, hey, Kevin, you know how to use this? Yeah, it's my first time. I thought I understood from James, but I'm missing some key thing here. So, well, let me stop sharing.
Sure.
So I've got this going.
Sure.
And I've got people on Zoom, and
Mhm.
I know there was the visualizer thing, but that didn't seem to be working, where I can't get that up there and have both people see it.
Right, right. Okay, well, let's see if we minimize this again.
Oh. Is it full
Yeah,
screen? Okay.
Yeah, because I was almost wondering if this is set up kind of like an extended view. So if we try like moving this window over,
Yeah, I can do
Okay.
that, but I don't really want to have
right,
them. Well, I can hide them, huh?
right.
Yeah. And then it's
So
back
that
over.
could be one option, or another one could be if we go into the settings in here, and we do, if we type to search, like do like monitor. Yeah, so it could be duplicate or extend.
I thought it was already set up.
Let's see. But then instead of extend, let's try duplicate. Well, we'll see. Oh yeah, so you can see here, like it's the exact same
Okay.
thing here as it is there.
So I want to keep those
Mhm.
changes.
Yeah.
Okay.
Which I might be messing it up for James here. but,
Sure. Then he could, yeah.
But yeah, so now it should be exactly what we're seeing here. Should
It's
be
on there, so
exactly
then
what
if
they see
I-
there. Yeah,
Okay.
and that should be exactly what the Zoom people are seeing. too.
Okay. And I'm not going to worry about people's names up there. That's okay.
Yeah, if that,
Yeah.
hopefully, fingers
Yeah,
crossed,
okay,
that's my
okay.
creative solution at least.
Thank you.
Yeah, okay.
We'll work with that for now. Thank you so much, Kevin. Sorry to bug you. Yeah. Okay, can everybody online see my screen? Sorry, I'm just gonna have to, well, can I move this part over? I don't know if I can. I'll worry about that later. So if you're online, just know that your comments I can kind of see. So if you don't want anybody to, everybody in the room can see it. But if you're asking math questions, that's fine. Okay, hi. This is stressful. Yeah. So I'm Grant, taking over for James. He's going to be back on Monday. And what he told me was, hello.
Good.
Yeah, Kevin came and saved me. Thank you.
Yay, okay. I got Sarah on the phone. just in
Okay.
case.
Thank you.
Okay.
I'm good for now.
Yeah.
So James said that I was here, you probably saw me in the corner, that you're talking about linearization, and that is typically the last thing in chapter 3. I know that in the syllabus, there's Newton's method and Taylor polynomials, but those are listed as optional things. How many people, did anybody do Newton's method? Okay, what instructor are we talking? The Dell, yeah, you like that, okay. What about Taylor polynomials? You did those too, okay. And then I heard that other people are working on finding absolute max min points, which is the next section. Okay, I'm seeing more heads nodding there. So why don't we talk about this? Because I did unfortunately waste a few precious minutes of time for the class. And then, Newton's method, Taylor polynomials, certainly I can help with that if you come to office hours. My office hours are listed on the AATC website as well, and you're all welcome to come. I've had them, it says 17B, 21B, and 21C, but I haven't been getting that many people where I couldn't handle more. So you're welcome to come, and if you want to, I can tell you about Newton's method and stuff like that. Okay, so the beginning of chapter 4 is talking about finding the absolute max and min values of a function on a closed interval. And so let's just take a look at some really simple graphs. And if we're asking for the absolute max and min points, we can actually sketch these. So this first one's just a line with a y-intercept of 1 and a slope of 2. And we're only interested in this graph on the very narrow window from 1 to 3. If x is 1, I can tell that this thing's going to be starting, my y value is at 3. And if x is 3 and I plug that in, and you see that that's going to be 7. So my line's going to look like this. And so when we talk about absolute max and min points. We're talking about the y values, right? For this little portion of the graph, what is the absolute highest y value? 7, yeah, not a trick question. And the absolute lowest would be 3. So we could say absolute, I'm going to abbreviate, absolute max equals 7, and that's happening at x equals 3. Additionally, we could list this as a point, right? We could say 3, 7, and my absolute min is 1, 3. I'm gonna write it this way though, equals 3, which is happening at x equals 1. So that would be like 1, 3. Pretty straightforward, right? When it's just a line. The idea is though, where we're going to be given functions that you probably won't want to graph. They're going to be ugly, and so we need to think about like how can we, without resorting to the graph, tell where our absolute max and min points are. But let's just start with this. And what I want you to note here is my absolute max occurred at one of my endpoints, right? And my min occurred at the other endpoint. That makes sense. Okay, how about something like f of x equals x squared on the interval from -2 to 3? That's just our parabola, right? I'm going over to 3 here, so it's going to be a little bit higher on the right side. And just by sketching it, you can pretty much tell that your absolute max is going to happen right here at your right-hand endpoint. And we could write that as 3. Let's just go ahead now on the coordinate here. 3, comma, if we plug 3 in there, that's going to be 9. So it'll be 9. But unlike the line, my absolute minimum, the lowest this graph ever goes to, is not at the other endpoint. It's right there, huh? It's right here at the bottom. Now, what's special about that point? Thinking about this is 17A, you've been talking about derivatives, right? Slopes of tangent lines. What's special about the vertex of a parabola in terms of the derivative? It's 0, right? So the derivative here is equal to 0. And that happens to be the lowest point here. So my absolute min is going to be 0, 0 on this one. So what we've seen now in this example is one of my absolute max points is at the endpoint. The other one was at a place where the derivative was equal to 0. Let's keep going. This is a graph. I don't know if you know this one. Do you know what the graph of x to the 2/3 looks like? It's one of my favorite graphs. One of my favorite graphs, because that's how I'm not a very good artist. Whenever I'm like playing Pictionary or something and someone asks to like draw a bird, this is how I draw my birds. I just go like this. The full graph looks like, well, if I started here, it goes like this, and it goes right into the origin, and then it comes out the other side like this. Now we're looking at this from the interval from -1 to 8. So this would be like has a much longer wing on this side here. Okay, so getting into this, where we're going to find absolute max and min. Don't give me a number. Where does my absolute maximum occur? At one of my 2 endpoints, right? Do you see that? Which has happened for the last 2, right? So my absolute max is still at one of my endpoints. It's going to happen at 8. And then just to remind you, right, if you want to do 8 to the 2/3, that means you take the cube root of 8 and then square the result. So you'd have 2 squared is going to be 4. And my absolute min this time happens clearly right here. But in terms of derivatives, this was the slope of the tangent line does not equal 0 there. That's a sharp corner. And I'm guessing early on this chapter 3, when you started talking about the derivative, you talked about the idea of a function not being differentiable. And do you remember one of the indicators of a function not having a derivative is there's a sharp point, right? You had that discussion. So, but that nevertheless, that is my minimum. And so my minimum is happening at a place where my derivative is actually undefined. But that still does give me my minimum. and that's going to be at 0, 0. Okay, so now we've found places where we can find absolute max and min points. I got one more, and then we're going to talk about this theorem that you've probably mentioned in class here. I think I can, okay, there we go. I can do this, maybe fit beginnings of the next one on there. Okay, now think about the graph of f of x equals x cubed. But notice what I did here, very slight change here. All the other ones I had a closed interval, right? But this one I have the open interval from -1 to 2. So graphically, what that means, can I pull this other sheet out? You know, the graph of x cubed usually goes like this, goes flat through the origin. I'm graphing it from -1 to +2. But when I cut it off at -1, it's going to have an open circle. Goes flat, comes up here. And at 2, it would have an open circle because I didn't indicate to include the endpoints. And we know, if you were allowed to plug in 2, that would have been 8. And if you were allowed to plug in -1 cubed would have been -1. So does this thing have an absolute maximum? And this is kind of a debatable question. Do you see that we cannot say that the function has an absolute max of 8? Why? Because it doesn't quite get there, does it? So then you might say, oh, well, it's 7.9. Well, doesn't this mean it goes to 7.99, 7.9999, right? It gets infinitely close to 8. But we cannot say that it has an absolute max that is a precise number. So we just say, you know what? This does not have, there is no absolute max. And the same thing would be true for your min, because you cannot actually get to that low point. No absolute min. Okay. Now, of course, that's because we didn't include the endpoints. If we were allowed to include them, then we would have had a maximum min, right? So what this is saying then, this is the extreme value theorem. Did you hear that in class? And give this a little more insight into this. For one thing, I didn't give any examples of this. All the ones I gave were pretty much continuous except at the endpoints. But you talked about continuity in 17A, and most of the theorems in the book from here on forward, 17A, B, and C, depend on a function being continuous. So that is part of the theorem. It does have to be a continuous function. And as long as you have a closed interval, let's say from A to B, then it's guaranteed you will have an absolute max and an absolute min. You can see why it has to be closed here, right? This wasn't closed, which means we don't have an absolute max or an absolute min. But you can draw any function you want to. As long as you have a closed interval, any kind of weird function, you are guaranteed to have an absolute max and an absolute min, right? Even if, what if you just drew a straight line, horizontal line like this, right? Well, you could argue that whatever this y value is both your absolute max and your min. There's nothing higher than, there's nothing lower than it, right? And the whole function has that same value. So I couldn't see that. That wasn't a picture. Okay, maybe I need to, no, I don't want to mess with the focus here. Okay, there's your extreme value theorem. It's guaranteed to have an absolute maximum. And then most of your homework is going to be, how do you find that maximum? Well, we got some insight into how we go about finding it in these last examples. Where is definitely one place, which we noticed many times, where your absolute max or min can occur. That's at one of your endpoints, right? So they can occur at endpoints, or we saw two examples that were not endpoints. Going back to example 2 and 3, we saw a place where the derivative was 0, and we saw a place where the derivative was undefined, that both corresponded to absolute mins. And so let's write that down. F prime of x equals 0, or F prime of x is undefined. And collectively, so we don't have to keep saying both of those, we're going to call this, you've heard this term probably in class, we're going to call these places critical points. Places where your derivative is equal to 0 or where it's undefined would be critical points. All right, so let's try it now. I think I'm going to go with this one. This one I think is a little bit less involved than the next one. So your typical homework would be, I should write the directions on top here. If I give you a function then and a closed interval, you should be able to find the absolute, there's a lot of terminology in this section. The term that kind of describes either an absolute max or an absolute min, we call those extrema. Extrema, that's like plural for extremum, an extreme value, right? A highest or a lowest. So if you see extrema or extrema, either way, that means absolute max and mins. We've got a closed interval, and we know this is a continuous function because both of these are individually continuous functions. So how would we approach this? Because I don't know what the graph of this looks like. Although that's where we're headed in this chapter, is graphing functions like this. We know for sure right off the bat, candidates for absolute max and min points are my two endpoints, huh? If it's going up like this, it's going to be the two endpoints. So let's check our endpoints, and what we're interested in is really the y values. So what we want to do is evaluate f of 1 over e and f of e. And this is e minus the ln of e. I thought I'd throw this in here because just to get some practice with ln's and e's, right? You're going to see a lot of them in the 17 series. Let's start with this. What's the natural log of e? That's 1. So this is just 1. Now, you don't get a calculator on this one, and I don't think you would need to necessarily. You should be able to, okay, now what's e? What's e roughly as a decimal? 2.7, right? 2.718, that's fine, 2.72-ish. As a very rough approximation, I even just use 3, right? It's a little bit less than 3. So this is going to be 2.7 minus 1. This is roughly 1.7, huh? How about this? Can I make some sense of that? If you see the natural log of 1 over e, you could always write that as the natural log of e to the negative 1. And what's the natural log of e to the negative 1? You can do it there's the inverse property is one way to do it. The natural log of e to a power is just the power. It's just going to be negative 1. The other way to do it, of course, is you could move the negative 1 down in front and then multiply by the ln of e, which is 1, right? Either way, you're going to get negative 1. So we could conclude that this thing now, if I use okay, I'm just doing estimation tools here. 1 over 2.7, I'm not going to be able to do much with, but if I say that's roughly 1/3 minus, and this is negative 1, I think we could say that this is roughly 1/3 plus 1, so 1 and 1/3, roughly. So as it stands now, who's my highest point? Which is bigger? This is certainly bigger than 1 1/3, huh? So right now, that's my candidate for my absolute max. And maybe this is my min, but what's left to check? Where else can absolute max min points occur? Where the derivative is equal to 0, yeah, or undefined. So let's take our derivative next. This is 1 minus 1 over x. And what I do is let's see if we can find out where that's equal to 0. Can you just look at that and see what's the answer for x? Yeah, x is going to be 1, right? This is equal to 0 when x is equal to 1. Now, it's also important to note that because we also talked about the place where the derivative is undefined. So my derivative equals 0. Here, I'm going to write f prime of x equals 0 at x equals 1. My derivative is undefined at what value? What would I plug in here and get something undefined? 0, huh? It would be undefined when x is 0. But why do I not need to worry about that? Well, a couple of reasons. Number one, the natural log is not even defined when x is 0, right? You can't even do that. But number two, I'm only interested, this is my world. I'm interested in the interval from 1 to e, 1 over e to e, and 0 is not in that interval. Is 1 in that interval? Yeah, right. That's about 1/3. That's about 2.7. So 1 is a number that I might have. That's a critical number. Okay, so this becomes both. Well, this is a critical number. And that is a candidate for my absolute max and min point. So what I would then just check is what is f of 1? The natural log of 1. Do you know that one? You should. Yeah. So one way to think about it, what's your base on a natural log? What's your invisible base that we don't write? Where can I write? I'll write it over here. So I'm going to write this bigger. Natural log of 1. Remember, your invisible base on a log is base e. And it's like saying, when you see something like this, it's like saying e to what power gives me 1? It's got to be 0, right? E to, the only power you could raise e to, so that would have to be 0. So anytime you see the natural log of 1, or really any log of 1, it's always going to be 0. So this gives me a value of 1. And then this is the cool thing about that theorem. On this interval, the absolute max min points has to be one of these 3 numbers. It's not possible to be any other number here. So I can make the call now that my absolute max is going to be at the point E here, right? It's going to be E. I'd probably write it exactly, not 1.7. I would say E minus 1, because remember, that's how we were approximating that. And my absolute min would happen at, well, 1 is smaller than 1 1/3. So it's just going to be 1, 1. Let's try another one. This one's gonna, the algebra is gonna get a little bit tricky here. Any questions? Oh, yes. Oh, because it's not in the interval. And it's not even not in interval. And it's not even defined, right? I can't take the natural log of 0, but I think that's the one to keep in mind though. If you get any critical numbers and it doesn't fall in your window of X values, just ignore it for now. Okay, so let's try this next one. F of x equals x times the square root of 4 minus x squared on the interval from -1 to 2. Probably recognizing the fun part's going to be taking that derivative and finding out where it's equal to 0. Huh? But I know already that candidates are my endpoints. So I usually do that first so that I can, first of all, not forget about it. So f of -1, if I plug in -1 there, that's going to be negative, that's going to be 3. It's going to be -√3. F of 2, well, if I plug in 2 there, that's going to be 0. So I know f of 2 is 0. So I've got my endpoints. And now what we need to do is look for any critical points. So we want to take this derivative using what you learned in chapter 3. What rule do I have to use to start this derivative? It's a product, right? And how many people see a chain rule in there too, right? Definitely. So, oh, how did you learn your product rules? Did you learn them in terms of U's with D's or F's and G's? Oh, good. Because I have trouble with. So if this is F and this is G, how did you learn your product rule? Anybody? Hmm. Oh, good. Perfect. Sometimes they flip this around, but I like it this way. A little bit easier, I think. Just move the prime along. Okay, so we have the derivative of x is just 1 times g, but I'm going to write that as 4 minus x squared to the 1/2 because that's going to help me take the derivative over here, plus x. And now the derivative of g, which is right here, that's a chain rule. 1/2 stuff, subtract 1, that's to the -1/2. Don't change the stuff, and then multiply by the derivative of the inside, which is -2x. And now I've got to find out where this whole mess is equal to 0. So there's a couple of ways to go here to think about how to simplify this. I could explain this to you using factoring, or I could explain it to you using common denominators. How many people want to see it with factoring? A couple common denominators. Not too many. Okay, factoring wins out. Okay, and I can mention both of them because you might not, when I show you the factoring, you might want to change your mind, and it's okay to change your mind. Because the kind of factoring I'm talking about here, I don't know if you've had practice with this, is factoring with negative exponents. What I would do first is this 1/2 and this 2, since this is all multiplication, we might as well just cancel that out. But in this term, I see a 4 minus x squared to the 1/2, and then I see a 4 minus x squared to the -1/2. When we factor, what power do we usually pull out? Like, for example, if I'm factoring x cubed plus x to the 7th, what do I pull out? X cubed. Why? Because it's the smaller of the two powers, huh? So what's my smallest power here? So I'm going to factor out 4 minus x squared to the -1/2. I'm going to put brackets here just to really emphasize that I'm factoring this out. Now the question is then, if I pull out 4 minus x squared to the -1/2 from 4 minus x squared to the +1/2, that's got to leave a certain power of 4 minus x squared. The question is, what power? Well, I can explain this a couple of ways. Let's go back to this example up here, x cubed plus x to the 7th. So if I take out x cubed from x cubed, that just leaves it with 1. But what power of x would be left here when I take out x cubed from x to the 7th? 4, right? And how do we know that? You could do 7 minus 3, huh? What I took out, 7 minus 3 gives you 4. Alternatively, you could say this plus this has to add to 7, right? So, but if I do the subtraction way, what this power should be, if you agree with that, it should be 1/2 minus -1/2. What's that equal? 1/2 minus -1/2. Not just 1, because you're adding, right? This is just going to be to the first power. And if that's bothering you still, how I could check it is if I were to multiply back in, what do I do with the powers when I multiply? add them, right? Negative 1/2 plus 1 gets me back to positive 1/2. So it's just to the first power. Okay, for the next term, I do have this minus, and I notice I still had an x and I still had an x there. So I'm going to end up with a minus x squared when I put these two together. And of course, the negative. Now that I've taken this out to the negative 1/2 and it's multiplied, where can a power go if it's to a negative power? Where can it now go? I'm going to bring that down here, 4 minus x squared to the positive 1/2. And whenever anything's to the first power, you don't even really need parentheses. This is just 4 minus x squared minus x squared. It's 4 minus 2x squared. This is my derivative. And what I want to do is figure out where this is equal to 0. A fraction's equal to 0 when which part is 0, the top or the bottom? Think about fractions that equal 0, right? 0 over 3 equals 0. 0 over 7 equals 0. What is 5 over 0? Is that equal to 0? That's undefined, right? You can't divide by 0. So anytime a fraction is equal to 0, it must be because the top is 0. So if I set this fraction equal to 0, what it means is 4 minus 2x squared has to be equal to 0. Divide by 2. And technically, I end up getting plus or minus the square root of 2. Now, it is important to note, because we talked about critical points can be where the derivative is equal to 0, which is both of these numbers, and where it's undefined. Maybe I'll switch. A fraction's derivative is undefined when the bottom is 0. F prime undefined when, can you just look at that? What two x values would make that undefined? How many people agree? 2, right? And also, if 2 works, what else works? Because you're squaring it. Negative 2, right? When x is equal to plus or minus 2. Now, these are all critical numbers, but let's think about what we need. Number 1, we already have 2, right? If I slide this back up, we've already checked 2. That's one of my endpoints. We've already got the value there. Number 2, negative 2 is not in my window, is it? So I don't really care about that. So I'm going to make a note here. Only need to worry about numbers in the interval from -1 to 2 in this case. So that's going to rule out certainly the -2. We've already got the +2. How about these two? How many people agree? -√2, isn't that like -1.4 something? That's not in our window either, is it? So I don't need to worry about -√2. I can not worry about that. But +√2 is a little bit bigger than 1, so that is in my window. So the net result of this, the only other number that we now concerned about is x equals +√2. And so what I would then check is what is the value of my function when x is +√2. I can't fit it on here, but remember my function was x square root of 4 minus x squared. If I plug in √2 for x, I get √2 there. And if I put in √2 and square it, that becomes 2. 4 minus 2 is 2. I end up with √2 times √2, which is just 2. So this becomes 2. So these are my candidates. Unfortunately, I won't be able to fit them on the same screen. Remember, my two endpoints were -√3 and 0 were my y values. And then this is my critical number. So 2 is obviously the biggest number. So this is my absolute max. And I have the -√3 and the 0. So this right here would become my absolute min. move that up. Let's see how far we can get in this next one, because I kind of like this one. The whole point of the 17 series is to see how this applies to your world in biology, right? Well, first of all, any questions on this? I know there was a bit of tricky algebra, but more about the process. But this question caught my attention. It's number 57, and I had to just paraphrase the information here in 4.1. It's talking about the virulence of a disease. And what virulence is it's not quite the same as like an R0 number, which is how contagious something is, but it's more about a measure of how deadly a disease is, right? Which is something I know last couple of years we're all thinking about, right? And this, if you have a virus that is very virulent throughout a population, with we'll denote P as a population size, obviously that's going to affect the size of the population, right? And so there's a model. This was given. This is all given in the problem. Someone came up with a model that gives the population size as a function of the virulence, how deadly a disease is. And they're telling us that V has to be some number between 0 and 9. I don't know how they get those numbers, but we'll just go with it, okay? So, and it's asking for what are the absolute max and min population sizes and the virulence at which they occur. So, same exact question. But there's kind of an interesting result when we do this. So let's check our endpoints first. If I have a virus that has a virulence of 0, means it's not really dangerous at all. It's really easy to see. Just plug in 0 there, I'm just going to get 10. So my population is 10. And my population, if V is equal to 9, it actually kind of works out nice. This is 19. 9 squares is 81. It ends up coming out to be 100. And the denominator is 10. It's also 10. We actually end up with the same population, whether the virus has a V value of 0 or 9. It's the same, it's 10. We kind of have a tie here. And that's one thing I liked about this problem too, is it's okay to have ties. If this ends up being the max, we can say it's a tie. You have a max of 10 at both of these V values. That's totally fine. But we also need to now check the derivative for any critical numbers. So let's take our P prime. I also picked this problem because it gives us a chance to use the quotient rule. Did James teach you the low D high thing, or do you? Okay, yeah. Because if you try to give it to me in F's and G's, I don't. So I got low D high. The derivative of the top would be 1 plus 2V minus the high. And the derivative of the bottom is just 1 over the bottom squared. And we're going to try to set this equal to 0. So we're going to have to, I don't see any fancy factoring here. We're going to have to just multiply this all out. So I'm going to have 1 plus 2V plus V. So that'll be 3V. And then I'll distribute the 10. Two V squared minus V squared gives me V squared. 3V minus V is plus 2V. 1 minus 10 is minus 9. Now, as we said before, fraction will equal 0 when the top is 0. It's going to be undefined when v is -1, but that doesn't make any sense, right? You don't, with the v, it doesn't have a value of a -1, so we don't have to worry about where it's undefined. But it's equal to 0 when the top is 0. I'm just going to write it down here. P squared plus 2 minus 9 equals 0. Now, unfortunately, what is that? You see a quadratic, you want to factor it, right? It ends up not factoring. What is your backup if it doesn't factor? Quadratic formula, yeah. So we're out of time here, and if you have to go, I totally get it. But if you use the quadratic, but no worries if you have to leave, you end up getting like one value of v that's like approximately, I did it before class. I think you end up getting like you get like -1 plus root 10, which is about 2.16. And if you plug this in, you kind of need a calculator. So for the plugging in part, if you plug in 2.16, you get a value, I think it was in the 5s. I want to say it was 5 point something. So this would have to be done on a calculator. And so that would obviously be my min, because that's lower than my two other values. That would be my absolute min. But what I think is really hopefully interesting to you is to think about why this happened. Why does this happen? If you actually graph this function, if you graph the population size as a function of the virulence, we saw that it had a value of 10 when v was 0, and it also had a value of 10 when v was 9. But what happens with the graph is it dips down like this and then comes back up. So this minimum we're seeing right here is happening when v is about 2.16. Why does that make sense? You've got a population and you get a virus, right? If the virus is mildly dangerous, what do you expect to happen to your population? Decreases, right? Now, the part that's maybe less intuitive, why does it go back up the more deadly it gets? Oh, possibly. Okay, I think this model is actually excluding like things like vaccines and antidotes. Yeah. Even without that, why does it go up as it gets more deadly? This is a good biology question.
I'm thinking it's like, wait, so the higher it goes, like the less deadly it is, or the more deadly it is?
The more deadly it is. Yeah, the bigger the net value for V, it's a more deadly virus. And if you've got a really, really dangerous virus, now why does the population go down, right? When there's a virus, is that we spread it, right? And people get it. But what happens if you've got a really, really dangerous virus? You possibly quarantine. And the big thing there, I just add to that, is they die off slow or fast. If it's a really, really deadly disease, they die before they can actually give it to somebody, right? And that's what explains why the population goes back up. Yeah, if you get it, it's bad for you, but you're probably not going to live long enough to spread it, right? So you would expect that kind of a curve to happen. So anyhow, I thought that was kind of neat just to apply it to something, so we're not just playing with random functions. But and yes, if you're online, thank you. I'm so sorry for it not going smooth today, but I'll work for Friday, try to figure this out. So and yes, okay. You're welcome. James said you all knew how to sign in, so I assume you did that. Okay. You can probably do it later. There's something on Canvas or something he said. Okay. Oh, it's your first time. Okay.
QR codes.
Is that what these are?
Yeah. You do on Canvas too. I always forget.
Oh, I can, yeah. Yeah, because it was a little bit, I guess, the other thing I'm not sure of is where does this recording go after I stop here? Why don't I go ahead and end the meeting and we'll see.